Welcome to the Antonio Zamora podcast that discusses a variety of scientific topics. Younger Dryas forensic analysis of ejecta blanket. Approximately 12,900 years ago, an extraterrestrial impact on the Laurentide Ice Sheet ejected a massive amount of ice chunks in ballistic trajectories with a range of 1,500 kilometers and triggered the Younger Dryas cooling event. The energetic secondary impacts of the ice chunks liquefied the sandy soil of the Atlantic coastal plain and created inclined conical cavities that transformed into shallow elliptical bays by viscous relaxation. This video analyzes the Carolina bays near Fayetteville, North Carolina to determine some of the characteristics of the Younger Dryas ejecta curtain using the temporal distribution of secondary impacts and the speeds and angles of the ice projectiles that made the bays. This is a LiDAR image of the Carolina bays 25 kilometers southwest from Fayetteville, North Carolina. The image covers an area of about 550 square kilometers. As indicated by the 5-kilometer scale at the bottom of the image, the Carolina bays vary from a few hundred meters to several kilometers in size. The terrain in the upper left corner has an elevation of 76 meters above sea level, and the lower right corner has an elevation of 16 meters above sea level. If you pay close attention, you will notice Interstate Highway 95, I-95, as a wavy line starting from the top right corner. The straight line running diagonally across the center is the CSX and Norfolk Southern Railroad line. The image is deliberately in black and white to bring attention to the two most notable geological features of the Atlantic coastal plain, which are the Carolina bays and the fluvial channels of rivers and creeks. Many university geology courses do not even mention the Carolina bays. One time, when I showed this picture to a professional geologist, he asked me, "Which planet is this?" We know more about the craters of the moon than about the ground under our feet because a widely accepted mainstream hypothesis, which involves a lot of hand-waving, proposes that the Carolina bays were created by wind and water mechanisms, and from this interpretation, it follows that the bays are as common and uninteresting as mud puddles. Pay attention to the bays labeled A and B along the railroad line. These bays will be discussed in more detail later. Since the discovery by aerial photography in the 1930s, the Carolina bays were described as either oval or elliptical. In 2001, basins with similar geometry were found in Nebraska. The axial orientations of the Carolina bays and the Nebraska basins converge by the Great Lakes. A paper published in 2017 conducted a geometrical study that found that the Carolina bays and the Nebraska rainwater basins are mathematical ellipses. The paper proposed that these structures originated as inclined conical cavities created by secondary impacts of glacier ice ejected by a meteorite impact on the Laurentide Ice Sheet. It can be shown experimentally that oblique impacts of ice projectiles can create inclined conical cavities. These images show an inclined conical cavity created by the impact of an ice projectile on a viscous target. When viewed from above, the conical cavity has an elliptical geometry, and the raised rims produced by the compressive forces of the impact are analogous to the raised rims of the Carolina bays. Now we come back to the large bays labeled A and B. Bay A has a length of 4,160 meters, which is 2.58 miles. Bay B has a length of 3,850 meters. We can appreciate the enormous size of the Carolina bays by comparing them to Meteor Crater in Arizona, which has a diameter of 1,186 meters. We now focus our attention on the large Bay A. This bay has a thin outer rim and an inner rim that tapers toward the thicker rim on the southeast end of the ellipse. The raised rims are overturned flaps created by the compressive plowing action of the ice projectile. Secondary rims are common when the ground is not liquefied enough for viscous relaxation to restore the stratigraphy. The double rims are also seen in experimental impacts, as illustrated in the inset. From the geological principle of superposition, we can deduce that the large Bay A was emplaced after the smaller bay labeled C. Here we see that the small bay can be fitted with an ellipse. Only 5 points are needed to mathematically fit an ellipse to a partially obscured bay. The large bay can also be precisely fitted with an ellipse. The dimensions of the ellipse can be used to calculate the angle of impact. The sine of the angle corresponds to the width-to-length ratio of the bay. In this case, the angle of impact is 30 degrees. Professor J. Melosh and Ross Bayer developed a program to calculate projectile size from crater diameter based on yield equations relating energy to crater size. The program requires the diameter of the crater, the projectile velocity, the angle of impact, and information about the physical characteristics of the projectile and the target material. There's a link to the calculator in the description of this video. The ruler tool of Google Earth can be used to measure the distance between any Carolina Bay and the site of the extraterrestrial impact in Saginaw Bay, which is the convergence point of the Carolina Bays and Nebraska rainwater basins determined by Michael Davias in 2010. Using the angle obtained from the width to length ratio of the ellipse and the distance from Google Earth, we can calculate that the ice chunk that produced Bay A had a launch speed of 3,498 meters per second and a loft time of 356 seconds, which is 5.94 minutes. The ice projectile reached a height of 155.9 kilometers above the surface of the Earth. This ballistic trajectory is classified as a suborbital space flight because Earth's atmosphere extends only to 100 kilometers above the surface. The program to calculate projectile size from crater diameter assumes that the crater is circular. By equating the area of a circle to the area of an ellipse, we find that the equivalent radius of the ellipse is the square root of the product of its semi-major and semi-minor axis. The diameter of the ellipse can then be used to calculate the projectile size. The program calculates that the ice projectile that formed Bay A had a diameter of 1,180 meters and energy of 1,250 megatons. A projectile diameter of 1,180 meters is an ice chunk bigger than 1 kilometer. The impacts that created the Carolina Bays had so much energy that they would have killed any animals or humans nearby. This is why the creation of the Carolina Bays has to be associated with an extinction event, such as the extinction of the North American megafauna and the Clovis people. It would have been impossible to survive the saturation bombardment by this powerful and horrific hailstorm. Compare the sharp borders of Bay A with the wider and less defined borders of Bay B. We are now going to shift our attention to Bay B and its smaller companion bays. The undefined edges of the large bay indicate that the ice projectile hit a stream and made a splash that created broader borders along the periphery of the impact cavity. The drainage channel in the northwest part of the bay may be a remnant of what was there at the time of the impact. The formation of the large bay was followed by many smaller impacts. Here we can see 3 small impacts on the rim of Bay B and an impact labeled D. Carolina Bay D has well-defined margins, a width of 688 meters and a length of 1,086 meters. The width-to-length ratio corresponds to an impact angle of 39.3 degrees. Using the same calculations as before, the projectile that made this bay had a diameter of 252 meters. The energy released by the impact was 10.7 megatons. Notice the loft time of 7.06 minutes compared to 5.94 minutes for the large Bay A. This difference of flight times makes it possible for ice projectiles with higher trajectories to produce impact scars on bays created earlier by ice projectiles with lower trajectories. This histogram prepared by Michael Davias shows the distribution of the bays based on their area. Most Carolina bays in this sample are smaller than 10 hectares, which corresponds to 100,000 square meters, or 25 acres. This LiDAR image shows Fayetteville, North Carolina and Fort Bragg in their geological context. The highlands show deep fluvial channels and the flatter areas show some streams and Carolina bays. The large bays A and B are marked to show their relationship to the urban area. This is a satellite image of the same area. The LiDAR image shows that the Cape Fear River channel has a width of 7 kilometers. This is very wide compared to the 100 cubic meters of water per second that now flow by the city of Fayetteville. In the past, there must have been a torrential flow of water to carve this wide channel. Where did all the water come from? A saturation bombardment experiment helps to answer this question. A container with a mixture of clay, sand, and water is subjected to impacts by ice projectiles. The projectiles form inclined conical cavities, and as the bombardment continues, the area becomes covered with the scars of the impacts. When the bombardment stops, the ice projectiles melt and create a flow of water that can create fluvial channels on the landscape. When the ice boulders that created the Carolina Bays melted, they released a large volume of water that carved the 7-kilometer wide channel of the Cape Fear River. Today, this channel is very small by comparison. Rockfish Creek carried so much water that it changed the course of the Cape Fear River into a big bend. The surface features of the Carolina Bays have been preserved because the sandy soil allows water to drain quickly to the subsurface where it then flows through underground aquifers. The Carolina Bays still hold many secrets, but the existence of the bays should not remain secret. All geology courses should teach students about the Carolina Bays because they are the most prevalent and notable land features of the Atlantic coastal plain. Challenge your science teachers. Print this image from the high-resolution link given in the video description and ask your teachers, what planet is this? Thank you for listening to this podcast. Please visit the YouTube channel or the website for many other interesting topics.